that you are given an array integer nums and an integer limit. So array nums and the limit, you are given two things. Okay, you have to return the size of the longest non-empty sub array such that the absolute difference between any two elements of this sub array is less than or equal to limit. There are many things which was mentioned. Let's break it down. So basically, if we go and break it down, which means we are going brute force way, we have to generate all these sub arrays. Out of all those sub arrays, I have to get, again, let's take one sub array now. For that one sub array, I have to take the absolute difference between any two elements of the sub array. In that sub array, if I take the absolute difference between any two element, that absolute difference, any two element in that, so n square are the sub arrays. For every sub array, I will have n square pairs. So finding the difference again would have been n square. So this line could also have been n square, but we know that such that the absolute difference between the two elements of the subarray is less than or equal to my limit, is less than. So I just want to know that the subarray which I have taken, the maximum absolute difference, if that also is less than equal to my limit, I'm good to say that every other difference, every other absolute difference will also be less than equal to limit. So I will do one thing. I modified this statement and said absolute difference between any two elements. No, absolute difference between two elements such that that absolute difference is maximum. So I took the maximum absolute difference, and that can be between the max and the min element. So if in that subarray I took the max and the min element, I took their difference, and again I can easily get the max and min of a subarray in O of n time. After getting that difference, I know that this is the maximum absolute difference of this subarray. If this is less than equal to my limit, then I am good to say that this specific subarray is good. If the subarray is good, then just maximize the length, else just ignore that and try for a next subarray. Now we know that this will take O of n cube time. We also know one very standard optimization of brute force. Again, although this is not brute force, this is because brute force would have been O of n square into n square. But then we thought, okay, O of n square into n will also work because we'll just take the maximum as absolute difference. Now, in that, the optimization again is that while, like, what you are doing, you are trying to find the max and min. That's the reason you are getting the O of n time. So while generating the subarrays itself, you can find this max and min while generating the subarrays itself. So that can help you and get O of n square as the complexity. But still, seeing the constraints of n square is also high. Now let's come on back and see what else we can do. But so far we saw one thing, that if I have some array, I have to for sure take sub arrays and I have to take the max and the min element. That is what I required. Now, if I had this specific array, I also realized that I am taking a sub array, so I can for sure use a 2-pointer or sliding window technique, kind of. Okay. The question is, that was a hint, intuition. I can use it, but can I use it or not? That's the actual question. Yes, I can use it. Why I am saying it? Again, you will only get this why only when you have learned that what was the why I have taught in this video. The why is that as we expand our window or our boundary towards right, our maximum difference will remain same or will increase. Now, other statement is as we contract or shrink the window from left, maximum difference will remain same or will decrease. And this was the prime thing of our 2-pointer when we can apply it. If we go towards right, it should linearly do one thing, either increase or decrease. It is linearly increasing, or again will remain same. That is okay for us also. But as we go towards left, as we move to move the left window, it should decrease stuff or remain same. And that is followed, and that is the reason I can simply apply my 2-pointer. Now, when I say, Aryan, how did you even figure this out, that maximum difference is increasing or not? Simple, bro. If you take this simple array, if you right now know the maximum difference, again, right now, let's say my window is this much, and I know the maximum difference right now is something, let's say X. If I encounter a new window, which means I just expand my window, I will get some new element. Now, if let's take this arbitrary values x, y, and z, and they were giving, let's say, the difference as, let's say, d1, and this is the maximum absolute difference so far. Now I just expanded my window, so either this element can be, again, expect, like, let's imagine that x is very small, y is big, and z is very big. So this element which I have right now put here, it can be either higher than z or can be in between x and z, because right now this difference would have been z minus x. This element which I put here would have been higher than z, let's say w. It can be in between x and z, let's say w. It can be lesser than x, which is w. In any case, when it is higher, so x and w, difference increased. When it is in mid, difference remains same, again x and z. When it is small, z and w, again difference increased. So that is the reason I say that, okay, as soon as I increase my window, for sure difference will either remain same or will increase. And the same way for as I shrink my window. Now I very easily know that I can easily apply my two-pointer technique. Okay, how will I apply it? Simple. I know that my 2 pointers have I and j. In my I and j, I will simply try to expand my window. Right now, I will say again, right now I will say that I will simply try to expand my window. But for that, you should be knowing how the template looks like. Template of our two-pointer, as we have already mentioned, looks like that we move our j, like while j is less than n, we try to incorporate j's behavior. Then while my I is less than j, or again this can be less than equal to j also, depending on the condition itself, and the condition is invalid. For you, the invalid condition is the maximum absolute difference, which is the difference between max element minus min element. If this is more than your limit, then you should shrink your window. Again, this I will name or alias it as diff. If this diff is more than your limit, then you should shrink your window, which means remove the incorporation of I and then shrink your I, and then basically update your answer, because you want to maximize your subarray length. Incorporate your answer and then move. Always make sure to move your j at every step. This is a simple two-point template which we have seen in the crash course. Now coming on back, let's apply that same template and dry run, because we know we can solve it. Just dry run quickly and see if we can do, or maybe we require something else also. Okay, so how to dry run? Simply, I have I and j. Okay, I will incorporate my j. Aryan, what do you mean by incorporation? Incorporation as in like how you will use it. Ultimately, your use was to finding the diff. Diff is between maximum and the minimum element. Okay, Aryan, I will just maintain what is max, what is minimum. Okay, as you showed in the above thing, I will maintain two variables. Okay, bro, good for you. Maintain two variables, max element and min element. If you maintain that, right now both of them are 10. Okay, you will expand the window. Okay, you go to j. Then you will simply try to update it. Okay, update the min element. Okay, you updated that. Okay, great. You will find the diff. Diff will be more. Diff will be more. Okay, you will try to shrink it, because diff is now 9. Your limit was 5. So you will try to shrink, which means you will remove the incorporation of I. And I can see that incorporation of I was the maximum element. So I will remove it. Remove it as in, what I should put here? 1, 0, minus 1, what? Let's put 1. It seems like 1, 1. So by naked eye, it feels like 1. But did you see a very, very big flaw here? Right now, my element was 10. And I was kind of removing its incorporation. Okay, what if the window also would have previous element as 4, which means my max element would still have said 10, min element is still 1, but the element now is 4. So removing the existence of nums of I, how will you remove 4? You don't even have a 4 here. So in this case, you miss many things. You will even again, what if you again got a 10? Like, how will you incorporate 2 10s then? So we realized that's an issue. Like, ultimately my aim was to get minimum and the maximum element, but I cannot just maintain variable for it. I have to actually maintain all the min and the max value, or like all the values, and then from those values, again, when I say all the values, I mean for a window, I have to maintain what all elements are there in the current window, and from that I will get my min and the max value. Now, very easily we have seen two things. we have to, from the group of elements, we have to grab the min and the max element. A data structure is, yeah, again, to grab the max element, I will use a max heap. To grab the min element, I'll use a min heap. Now, other data structure which we can use is a multiset. Why not a set? Because the elements can be repeating. I want to take that also in consideration. So I have to take a multiset. Okay. So it feels like we can use both of them. Okay. It feels like, yeah. Now, so what we have realized is that is to grab the element. That is, we saw to grab the min or the max element. But after grabbing, okay, and putting that in my data structure, I can easily be able to derive my diff, because I will be easily able to grab my min and the max in log n time. But removing also is a factor. You have to remove your nums of I. You are at nums of I, you have to remove it. But removing in a priority queue Aryan, you can only remove the max or the min element, which means ideally priority queue also will not work here. Oh, okay, maybe not. I'm not putting that much brain, but I know multiset will for sure work, because multiset removing is very easy. So I will use multiset right now. Okay, I did not put that much brain. I did not even think of if I can solve it or not, but I thought, okay, let's try with a multiset. Okay, I will use a multiset, and that will help me to remove any element, because for me, I had to remove the existence of nums of I. Let's now do that simple trial and quickly solve it. How? Initially, I and j is here. Multiset will contain 10. I know I can simply move my j. Okay, as I move my j, I will firstly have to incorporate as in I will put this in my multiset 1. Now I will have to find the diff. Diff right now will be max minus min. Max is 10, min is 1, my diff is 9. I have my limit is 5, so I have to shrink. If I shrink it, so I have to remove 10. I will remove 10. I will shrink my I. Okay, then it will go on. Okay, right, then my j again will expand. I will put a 2. Diff will be 1. My max and min diff will be 1, less than limit. Okay, again expand. 4 minus, again a 4 will come in picture. 4 minus 1, again the diff is 3, less than limit. Again expand. Again, remember, every expansion will give you a answer length. Again, answer is the maximum length, which is being maximized. So far, when the j was here, you would have maximized your answer by saying answer equal to maximum of answer comma j minus I plus 1. Or you can also say with the length of the multiset. Both are okay. Okay, so far the answer you can see as would have been 3. This is the length, which is 3, which is correct. Okay, as you try to expand j, you will encounter a 7. 7 minus 1 is 6, more than the limit. Shrink it. Okay, I will shrink it. So I will remove 1, move my I. Now 7 minus 2, which is 5. Oh, it is equal to limit. Okay, good. So you see the again answer still was a 3. Again, try to expand it. Okay, put a 2 again. Again, max minus min, diff is 5. Valid. Maximize your answer 4. So this is your maximum length of the subarray which followed your limit, and that is the reason you can simply return the answer. As you can see, if I go back for this test case, the answer was a 4, which is this specific length. Cool. Let's see the code. It's exactly same template of our 2-pointer. The simple template says grab your I and j as 0 and 0. Again, maximum length is the answer. Remember, it's the answer. It's the answer. Then while j is less than n, I will incorporate my nums of j. I will find the diff, which is max element minus min element from my multiset. Then while my I is less than j and the diff is more than the limit, so I should shrink my I. How I will shrink my I? I'll grab my nums of I, remove that from my multiset, and then find the diff again. I'll grab that from my, I'll grab the nums of I from my multiset. I'll increase my I. I'll grab the diff again, and we'll keep on repeating it until my diff becomes less than equal to my limit. Now, as soon as it will get out here, which means I and j are the correct locations where the diff is less than equal to limit. So in that case, I can either take my multiset size, or I can also put that as j minus I plus 1. Both will work correctly. And ultimately, make sure to always keep on increasing your j at every step. Ultimately, return your answer, which is maximum length. Now, although you use 2 pointers, but because of using a multiset, your complexity became n log n. And again, multiset will store elements, so space will be also O of n. Now, can you improvise it? Maybe, maybe not. But one thing, like before even going, what we saw earlier, we also again we are just drilling down back onto what we saw or what we thought of when we were trying to grab min and max. We also thought of that maybe we could have applied a mini per max heap, but the issue was that Aryan, how will you handle the removal of something, removal of some element? So in that case, okay, that is one thing, how will I handle the removal? But the other thing was, if I encounter an element, in which heap I should put in, like, because I have to grab the max of the min element. So if I encounter a 10, the question is in which heap? Although for sure, if I have to grab both min and max, so I have to maintain two heaps, min heap and the max heap. But the incoming element, in which heap I will put this element? So I was confused. Should I put in a max heap, but then min heap will be empty? Should I put in min heap, but then max heap will be empty? Should I put in both? Maybe I can put in both. So okay, I was confused on where to put, so I'll put in both of them. If I put in both of them, I can easily be able to drive the diff, which means grab the maximum from a max heap, grab the minimum from the min heap, and I will simply get the diff. That's very easy. But if we see the code, which means the while loop, which we had seen in the earlier 2-point approach, if also, that will also work. But as soon as I will land inside, I will be confused, because ultimately I had to remove something. That something technically mentioned remove nums of I. But in this case, in this scenario for me, I don't even know. Or even if I know what I is, I would know nums of I is, but I cannot remove that nums of I, which I want. I can only remove the nums of I which is visible at the top of the priority queue. Oh, that's one thing. So with that, I realized, oh, am I missing something, or I'm basically doing something extra? Yes, I was missing something. The missing thing was the diff right now. It exceeded the limit because of this. Again, imagine this as a min heap, and imagine this as a max heap. So the diff was higher than the limit just because of the minimum element was very less, the maximum element was very high. So obviously it makes sense that I should, again, when I say I have to slide my window, which means I have to expand, shrink. Now in this case I am shrinking, which means I am removing some element. So it makes sense that if this is a min heap, so the first element is small, the next element will be large, the next element will be large. This is how min heap will be designed. The max heap will be, this element will be large, this will be smaller, this will be smaller. So that is how max heap is designed. Now in this case, it feels very ideal that because of taking the top elements, which means the minimum element and the super maximum element, I was getting my diff as very high, which means higher than limit. So it makes sense to either remove this minimum element or remove this maximum element from my min heap or the max heap, and then when I remove it, I'll get a, from min heap I get a higher value, which will make my diff less. Or if I remove my max element, so from max heap I'll get a smaller value, which will help me reduce my diff. So ultimately, this is what I thought, that this can decrease my diff if I try to either remove my max element or my min element. But this is what we thought of. That's good. But is it the nums of I? No. Nums of I was the I, as in nums of I. I was the extreme left. I told you again, this min and max could be the middle elements also. So it could have happened that it is 2, it is 9. Your nums of I was ideally here. Your I was ideally here. And let's see your j is here. So let's say it is 5. This is your min and max. But ideally, you should remove this also, na? Yeah, that's the issue. How to handle this? Simply. This is that case itself, that this kind of scenario in which the middle element is actually inside your heap, min and max, but you are landing onto the specific I itself. So you have to take this also in consideration and remove this. But from your min heap, you cannot remove element which is not a min or a max. How to do this? Simply, you simply realize one thing, that I don't even care about them anymore. Why I don't care about them anymore? Because I know that the actual disturbance is given by these two elements. So I have to remove and shift until I get this disturbance sorted, which means I don't even care about them. I have to keep on shifting until my disturbance is gone. My disturbance was given by this min and this max element. So to get rid of this disturbance, I have to at least get rid of min or the max element. Then only again, which means I will shift everything such that I get rid of this disturbance, which is 2. Now, it could also have been a case that 9 would have been here and 2 would have been here. So I have to get rid of the max. So I realize that I have to ultimately get rid of the disturbance from either max or min. Thus, what I will do, I know that min heap will keep the minimum element. I also need to know the index of the minimum element. This is the index of the minimum element. Let's say small m I. This is the index of the maximum element, which is big M max element. Again, from max heap top, I'll get a max element, and that's the index of that max element. I know that I have to keep on shifting again. I have to keep on shifting until I discard that again, either my max index or my min index. And I showed this because it could have also happened that 43296. So it could have also happened that whichever index is small, either your min index, min I, and this is max I. Either your min index is less, then discard up till your min index. If your max index is less, discard up till your max index. Ultimately, just getting rid of this min max pair. That's your ultimate aim, which means ultimately check whichever is minimum, max index or min index, whichever is minimum, check that index. Now your new index will be just again, because it could have also happened that there could have been a gap. 6 would have been here and 2 would have been here. So it's a still gap, right? So I have to reach on to just after this index. So my new index I would have been this, right? Which means I have to remove every element from my heap, either max or min. I have to remove every element from my heap, which is having index lesser than or equal to my max of I, or you can say minimum of either min heap index or max heap index, max heap top index. You have to remove that, and thus you'll get the ultimate new index I, which is your new valid index for trying again. So now what you did, you realize that you not only need your heap, which is min and the max heap, but you also need the corresponding index of that also element also, because min in the max heap will contain the element, but the index you also need. If you also need the index, which means that in your data structure now, this is how your min heap and max heap should look like. Now let's quickly have a dry run, that how we will solve it. Now we realize that we need to maintain the pair 0, 1, 2, 3, 4, 5. Now I have to maintain the indexes also, that for every incoming element I will maintain the indexes. Now let's simply quickly maintain that. Firstly, I will get a 10. Okay, you will push the number again. Remember, this is your min heap and this is your max heap. So you pushed a 10 and a 0. You pushed a 10 and a 0. You got both the elements, max and the min. Diff is 10 minus 10, diff is 0. So I can simply move my j. Okay, move my j. Push in both the elements. In the min heap, I will push, I'll get a 1 and a 1. In this, I'll push in, I'll get a 1 and a 1. Now again, grab the max element, 10, min element, 1. Diff is 9. I have to shrink it. Okay, shrink it, but how shrink it? No worries. Shrinking, get the minimum index from the min heap top element, min heap min element, grab the index, which is 1. Grab the index, which is 0. So I have to, this is my index. So this says again, minimum is 0. So I have to shift until this is broken. So my new I should come here. So my new I should come here, which means if my new I is here, so any I, which is any index which is less than my 1, I should remove that from my heap. Less than my 1. Okay, and again, removal is only happening from the top elements. So I will remove again. I will not be able to remove from the max min heap. Nah, it will still remain there, but I will remove that from my max heap. This is now gone. Okay, now expand it. So you see, this is still remaining in the main heap, but that will never impact my answer because it is min heap. Min heap, bottom elements are always ignored. Now move your j. Move your j. As you move your j, incorporate in min heap. Okay, incorporating that in min heap, I will have a 2 and a 2. Incorporate in max heap, I will have a 2 and a 2. Again, the diff 2 minus 1 is 2 minus 1 is 1. Less than limit. Okay, no worries. Expand. If I expand, j is here. Again, incorporate that 4 comma 3. Incorporate that again in the max heap 4 comma 3. Diff 4 minus 1. Again 3 less than limit. Okay, again expand. Make sure, never forget, मकसद नहीं बोलना है. Expand always. Before expanding, always make sure to maximize your answer. So I am not writing that, but I know that you will maximize yourself. You are good na? Yeah. So again, my next element comes in 7 comma 4. Okay. Again, in this max heap 7 comma 4. Now diff 7 minus 1 6. Shrink it. If I say shrink it, shrink up till what point? No worries. Minimum of my index, min index 1 or index max index 4. Minimum is a 1. So I have to shrink, and then new index will become a I plus 1. So this should become a new index, which means everything having an index lesser than index 2 should be removed. I will remove this. Okay, from this I can remove. No, it is 4, so I cannot remove. So I'll only remove this. Okay, no worries. Now again check diff 7 minus 2. 7 minus 2. Diff is 5. Okay. If it's okay, simply expand. Sorry. Yeah, simply expand. If I expand it, I will push in 2 comma 5. This is the min heap. So this 2 will go below it. 2 comma 5. Now again max heap 2 comma 5. Again 2 comma 5. Okay, find the diff 7 minus 2. It's okay. If it's okay, expand. Oh, my j has ended. I'm good to say this is my answer. So if this is my answer, I know that my max length would have been this one. Now this you can see. Again, look at the state. I did not remove every element. I only removed from the top, and that's what I use my indexes for. Cool. Let's see the code. It's exactly same as what we saw. Again, same I and j, same max length to maximize my answer. I use a max heap and a min heap. The only thing is that now I have element and the corresponding index of the element also. Now while j is less than n, incorporate your j, which means push your nums of j in your max heap and min heap. When I say push, I mean push the pair, nums of j and the corresponding j also. Same way, I will find the diff. Diff is simply grab the max element. Again, this is the max heap top, and first contains the element itself. Second contains the index of that element, and then grab the min element, which is the min element itself. Now when this diff is there, check if the diff is more than your limit, then you have to shrink it. But shrink it up till what point? Simply check your min heap index, check your max heap top index, take the minimum index, and this will plus 1 will say this will become your new index I. This will become your new index I. If this is your new index, so check the top of the max heap. If the top index of the max heap is less than my current new index, so keep on removing that from the max heap. Same way do for min heap. If the top index of the min heap is also less than, then also remove that also. When removing this, again find your diff again. If this diff is again large, keep on repeating the while loop, and ultimately getting the maximum length. Always make sure to update your G++. With this, Aryan, why you taught us such a hard method, and that too because it is harder than multiset, right? It is much harder than multiset, yeah. But Aryan, complexity is still same. Space is also still same. Why did you taught it? Please hold on for a minute, because the next optimal approach we will see by just seeing what we saw in this priority queue approach. Because again, we applied so much brain in priority queue, for sure we can use that brain, right? Yeah, we will use that brain. Just quick recap of what we did in priority queue. All these steps writing, and then utilizing those steps power to get our answer. First thing, we maintained our max elements in one data structure, which was max heap. This this helped us to maintain the data structure, maintain the elements in the order, in the max order. Then we took one more data structure to maintain the minimum elements, and that maintain the order in the minimum elements. Okay. Then we want something which can remove the elements fast, and we were only removing from the top of the priority queue. Again, I don't need to remove technically all the elements. I just need to remove the topmost element fast. Okay. I have to find the mid, which means, sorry, I have to find the diff. To find the diff, finding minimum and the maximum in very less time should be possible. Okay. Then I was ultimately trying to find the new index. New index was based on leftmost index from your max or the min heap, and ultimately remove all the indexes which are lesser than your this new index I. Now let's look at every point and see what all we need for every point if we want to use some other data structure for it. Remove indexes less than the new index, and that too, keep on removing should be a very less time. Considering I don't know what the current data structure is, and I cannot use any data structure which sort the elements, which means I cannot use a set, multiset, map, like I cannot use all these data structures. The best I can do is I can use a simple array. That's the best I can use. Now, simple array seems good, and it can also work by saying, Aryan, I will use a simple stack kind of a thing, or a simple queue kind of a thing, because I ultimately need to maintain the elements in the order. I represented it as index. I will maintain the elements in the order, which means the incoming element I am getting. This is firstly maintaining a order. I'm maintaining the max elements. I'm maintaining the min elements. Why did you show max like this? Because see, bro, whatsoever element I'm getting new, I will push in the end, and whatsoever max element I want to get, I will push it from the front. See, so with this, but Aryan, why do you need like this? Why can't you take one data structure and then can do both of them? Firstly, you cannot. Secondly, the prime thing for you is grabbing the leftmost index. So I have to grab the least indexes, and for those least indexes, I have to grab the corresponding max and the min values. The new indexes which are coming in, the new elements which are coming in should be pushed at the end, which will say the indexes are in order. And this indexes are in order will also help us by removing the indexes, because if I know the indexes are in order and I have to remove the indexes up till, let's say, index 2, I have to remove. So I'll remove all of them. Remove all of them. So removing will also be easy. Putting element in the back will also be easy. Copying element from the front will also be easy. It's just that maintain a decreasing and an increasing order for the corresponding data structure, which means I have to, again, this shows pushing, popping from one side, again, pushing it from the end, popping from the front. Seems like that I can use a queue, but there's one thing, that if a new element comes in, which is, let's say, this, which is let's say higher, which is, let's say, again, this is at this level, let's say, which means to maintain this order of decreasing, you will have to remove these elements also. You have to remove these elements. So other operation required in your data structure should be that you should remove from the back also. So in your queue, you can push from the back, remove from the back, and also remove from your front, or you can say view your front also. That is the reason I will have to use a DEQ. So I'll use two DEQs. One is max DEQ, another is min DEQ. And these two will help me two things. Firstly, pulling up the maximum and the minimum element in O of one time. Pushing in any new incoming element inside my DQ again in O of one time. But Aryan, you showed recently right now, right, that you will remove some elements. But yeah, element will be removed only once from any queue. This, if I equal to 3 was removed it will never come back because I'm currently at I equal to 6 and I'm only going forward. So every element if removed will be removed only once. And then, okay, with Deque, I was able to get the maximum element, but it also helped me get the latest index. And that index was required because of the strategy which we used in our min heap approach. Now with this fashion, it feels like Aryan, and this is still a quick doubt on how I will maintain these orders. No worries, let's quickly try run again. This is the third time try run, so एक like तो बनता है भाई. Cool. Now what we'll do again, main aim is मकसद नहीं बोलना, your main aim was to maintain these DEQs. Let's maintain this max DEQ, maintain this min DEQ. Firstly, same way as we did again. Remember the same way you did for your heap. Same way you did for your heap. Firstly, getting indexing. Firstly, putting the indexes. Okay, awesome. Then pushing. You pushed in 10. Again, make sure this should be in this order. That the extreme leftmost should be high. Should be like not voila high, but like should be high enough. Like not okay. Should be large enough that I should be able to remove it. As in like I should put it in the end, so that I can remove from the end maximum element. That is the use of my max DQ. And again, I will maintain my min DQ as that in my extreme left, I can remove something from the left and that should be minimum possible. This is what I have to maintain as the order. Okay, right in the very beginning, push 10 and 0. 10 and 0, push that in my min DQ. Now, grabbing the diff. Diff will be simply 10, 10. Diff is 0. Okay, expand your J. Expand your J. As you expand your J, you will incorporate a 1, 0. Can I put 1, 0 here? Yeah, it is a decreasing thing. I can put a 1, 1. I'll put it here. Can I put a 1, 1 here? Can I put a 1, 1? No. No. Why? Because I want my previous element should be lesser than me. Should be lesser than me. So I have to remove it. Okay, removing it, which means this will be 1, 1. Okay, good, great. Now again find the diff. Diff is 10 minus 1. Diff is 9. More than shrink. Now for shrinking, we realized right now I is here. We realized for shrinking we want the index of what? Index of up till what point to shrink. So I'll grab the index. Grab the index. Index is 0. Index is 1. Grab the min. Min is 0. So you have to shift up till min index plus 1, which means up till 1. So any index which is lesser than I should be shifted. So I will simply remove it. Again, is this lesser than 1? No, it is equal to 1. So keep it here itself. Now, okay. Move on. I know it's hard for you to move on, but still, move on. J. Okay, incorporate that. If I say incorporate that again, always push in the end of your DEQ. If I say incorporate that, it is J. 2, 2. Incorporate that. Can I push a 2? Next element I am putting is a higher value than 1. I have to remove it. Okay, no worries. 2, 2. Can I push 2, 2 here? Yeah, it is higher. Yeah, I can push 2, 2. Make sure I am referencing the diagram below. That is what I have to maintain. Okay, no worries. Move on. J. 4. Again, always make sure to find the diff. But here we can see that diff is 2 minus 1, which is 1 less than the limit. J. Incorporate the J. Can I push a higher value here? No. 4 is higher than the 2. I cannot push it. Remove it. Put a 4, 3. Okay. Here I can push it higher value. Yeah, I can push a higher value. Okay, 4, 3. Now, again, move on. Again, remember 4 minus 1, 3 less than limit. I'm good. Again, getting a 7. Can I push a higher value? No, I have to remove it. I'll push a 7, 4. Can I push a higher value? Yeah, obviously, yes. 7, 4. Push it. Find. Again, as you can see, you will find the diff. 7 minus 1, 6. More than limit. Shrink it. Shrink it as in, okay, shrink it. For shrinking, you have to go and find your minimum index. 1, 4. Minimum is 1. So new index can be 2. So new index will be 2. So every index which is lesser than 2 should be removed. Lesser than 2? No. Okay. Lesser than 2? Yes. Remove it. Lesser than 2? No. Okay. Keep it. Okay. Expand your J. Expand your J. 2, 5. It is, what happened? Oh, by 40 minutes away. Okay, I'll quickly wrap it up. J, you got a new index 2 less than, okay, 2 comma 5. I'll put it here. Can I put a here 2 comma 5? 7 is higher than my 2. I have to remove it. I can only put in like values which are equal or higher. 4 is still higher than 2. Remove it. 2, okay, equal to. Okay, I can put a 2 comma 5. Okay, great. 7 minus 2, again 5 equal. Okay, expand it. Expanded J, end it. Thus, by using my DQ, I was able to replicate my min max thing, finding diff easily and thus getting my answer. Again, make sure to maximize the answer at every step. Answer would have been maximized at every step. Cool. Now let's see the code. It's exactly same as what we saw in min heap. I will maintain a DEQ of pair of int. Again, a quick spoiler alert, you can solve it by using an int also, but it is totally up to you if you want to solve it by or not. But I want to relate it with the existing case which we saw. That's the reason I just took this as a pair also, but you can solve it by simply using an int also. Now I did the same thing, that I took my max DQ, and if the element I am getting right now, if the first element, as you can see, if the incoming element I am getting is higher, so I have to remove all the elements which are small, because I can only put a small value in my max DQ. I can only put a small value in my max DQ. So if the incoming element is higher, keep on removing from the back. Keep on removing. So you should keep on removing stuff, and then ultimately make sure to push also in the back. Why in the back? Because you have to maintain the order of indexes also. Same way, repeat the same stuff for your min DQ, that if the incoming element, I can only put the incoming element if it is higher. If it is lesser, I have to keep on removing from the back. So if it is lesser, you should keep on removing from the back in the min DQ, and then ultimately push in the back in the min DQ. Now when this is done, you have simply pushed the new incoming element, which is nums of j. Now find the diff. Simply grab from the front of your max DQ, grab from the front of your min DQ, and that will be simply your diff. Okay, when this is done, let's go and find your actual and check. If your diff is higher than the limit, find the index, which is the new index. Why index? So I'll simply get the front index from my max DQ, get the front index from my min DQ, add a 1, it should be my new index. Anything lesser than this index should be removed. So anything lesser than this index in my min DQ or my max DQ, I will remove it. And again, this is I'm comparing from the front, so it should be removed from the front itself. Ultimately, check the diff again and keep on repeating until your diff is high. Ultimately, if you are out of this loop, which means your diff was less than equal to your limit, so you can optimize or maximize your answer. Update your answer, and with this strategy, you used a DEQ, and thus your time complexity will be O of n. Space, again, it's a bit painful, but space is also O of n, but time is reduced to O of n. And that is the strategy for you to think of this thing. Again, this is not that easy. That's the reason I put it as medium hard. I don't know how this is medium, but this is actually medium hard because of the most optimized approach. If you would have thought of just this multiset, it is the easiest one. It is very easy. It is easy medium if we go about multiset approach, but going about priority queue, it becomes medium. Priority queue and then DQ, it becomes medium hard. Cool. I hope you got it. If yes, then please do smash the like, baby. And yes, सब तुम कर नहीं रहे हो, subscribe तुम कर नहीं रहे हो, पता नहीं क्यों यार, दिल से बुरा लगता है. Cool, bye, take care. Do join Discord for updates and for contests and for being a regular. Bye bye, take care. Bye bye.